session without further delaying. And once those who are present, please write your roll numbers in the chat box. I am going to present a note today, and on this note, as you can see that 3 topics name has been written. One is discrete random variable, another is binomial, and another is Poisson. So I'll quickly go through them. I hope you will understand. And if any board work is required, then I'll only do the board work, otherwise not. Now, discrete random variable has already been discussed. Random variable is a function whose domain is the sample space. Sample space is the set of all possible outcomes. And it's a function from the sample space to the subset of set of real numbers. We already know this. And the random variable, if it is discrete, that means that the functional values are finite, or even if they are infinite, they are countable. Otherwise, the functional values are termed as continuous. We shall only discuss right now with discrete random variable, and you already know that with respect to a discrete random variable, there is a probability distribution which is called discrete probability distribution, and the probabilities corresponding to that is called probability mass function. Now, discrete probability distributions are of various types. I shall discuss 2 types of discrete probability distribution in today's class. One type is called binomial, and another type is called Poisson. Binomial distribution and Poisson distribution. To understand these distributions, let us try to discuss the following situation. The case is, it's called a digital channel problem. What does it say? It says that the chance that a bit transmitted through a digital transmission channel is received in error is 0.1. Okay. Also assume that the transmission trials are independent. Let capital X is equal to the number of bits in error in the next 4 bits transmitted. Determine probability of X equal to 2. Now the random variable they have already defined. The random variable is defined as the number of bits in error in the next 4 bits transmitted. So 4 times the bits will be transmitted, and you are going to count how many times the error is occurring in this digital transmission. So random variable has been defined for you. It's a very practical problem, and we are going to see what is happening over here. Now, the solution. Let the letter capital E denote a bit in error, and let the letter capital O denote that the bit is all right. That is, the bit is having no error in it. Okay. So we can represent the outcomes of this experiment in the following way. And you see the possible cases in which we get sometimes the error bits, sometimes only the non-error bits, and sometimes a combination of both of these two in the following manner. So here I have tabulated all the possible ways by which these bits can be arranged with errors and without errors. So for instance, the first sequence, as you can see, where only O's are present, that means all the bits which has been transmitted in the first case, they're all okay. And where all E's are present, they are not okay. And in between them, sometimes the error bits is occurring once, sometimes it is occurring twice, and sometimes it's occurring thrice. So in this manner, all the possible outcomes have been tabulated. And you know how to calculate this kind of outcomes. How many outcomes are there? 1, 2, 3, 4, 5, 6, 7, 8, 16. How does it come? Since there are only 4 bits, we are going to count. 4 bits are transmitted sequentially. So total number of outcomes will be 2 to the power 4, that is 16. Okay. The event capital X that has been defined is equal to 2. Now, event is what is event? Event is a subset of the sample space. Now, X equal to X is the random variable which is counting the error bits in this uh, transmitted 4 sequence bits. So we have to define that what sort of events we are dealing with, first of all. Now, as I told you in the very first class, that no probability is justified unless you define the sample space, unless you know how many points are there in the sample space. So once the sample space is known to you, then you know any subset of the sample space is called the event. So definitely it tells us that when I'm counting X equal to 2, or I'm interested in X equal to 2, that means I have to extract out a subset from out of this sample space. So capital A is there. And you see, since I'm interested in counting error bits whose number is exactly equal to 2, so I will select only those sequence of 4 bits where only 2 errors have occurred. So in my event, which I denote by capital A, no such sample elements like O 4 times occurring. It is not present over here. I have considered only those from this chart where only 2 error bits are present. So every time you are going to see 2 error bits, EE here, EE here, EE there, and so on. So how many error bits are present? Let us count just for our sake of understanding. So we have got out of 16, we have got, according to our choice, we have got 1, 2, 3, 4, 5, 6 such cases. Now the trials are the sequence by which these bits are being transmitted or are being received. This sequence is, in this sequence, actually there are 4, one after another. Your machine is getting the bits. One bit is obtained, and then another is coming, and then another is coming, and then another is coming, like this. And every time you are going to see beep, 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 like this. Okay, or some red light is indicator is there, which is flickering. Okay, every time a bit is received. So the bits which are coming in your receiver, and the bit after that, and the bit after that, they're all, you can easily say that all these things are what, independent of one another. So if I consider one such sequence, for instance, probability of OOEE, say, if I want to calculate it, and if, as we know that each of these elements, each of these events, single events, OOEE, these things are independent of one another, and you know that for independent events, probability of A intersection B is equal to PA into PB. So I can write this as probability of O into probability of O into probability of E into probability of E. And the probability with which an error bit is received, this probability is given to be 0.1, and therefore for first 2 cases it is written as 1 minus 0.1, and for the last 2 cases it is written as 0.1. If I multiply, we get 0.0081. At this stage, I want to tell you something that as you can see, we have written it in this manner, OOEE. Don't think that all these events have been multiplied. Events cannot be multiplied. In between, intersection sign is there. But if you are dealing with so many things, so many intersection sign will come and the thing will become clumsy. So sometimes probability of A intersection B equals to PA into PB. It is written as probability of AB is equal to PA into PB. So AB sometimes takes the position of A intersection B. Okay. And since these are the possible cases, now this sequence, if I talk about this sequence is in this sequence, the 4 events are present individually. They are independent, but altogether, if the sequence is considered, this sequence, if you are going to get, then you are not going to get other 5 sequences. So the occurring of one such sequence of this form is excluding the chance of occurring the other types. And therefore, each of these 6 sequences are actually mutually exclusive. So we can get error bits in the following manner. We can get either this or this or this or this or this or this. And you know, when these things are mutually exclusive, probability of A union B equal to PA plus PB, and therefore we have written all these. And in each case, you are going to get the probability 0.0081. So it is getting multiplied by 6, and we are getting the probability as 0.0486. And we are done with the problem. What is the alternative approach to the situation? Now, in alternative approach, we can think of the following scenario. Say, for example, you see how many times you are going to get the transmission 4 times. So we are counting the number as n equals to 4. Okay. The probability of success, I'm introducing a term which is called probability of success. Probability of success is what? Success is achieved according to the situation. The success is achieved when an error bit is received. Do not think that since you are dealing with error, that is not a success. It should be a failure, not like this. We want to find out error because we want to rectify the thing, some sort of thing. It may so happen. So in my situation, the getting of error bits is the success. What is that probability of success? It is given to be 0.1. So I'm noting it down. So I am this 4th transmission, I am denoting this 4th transmission by small n in general. And I'm denoting this this probabilities in each case by small p, which is 0.1. Now, if I want to find out what is the probability of x equal to t2, then you see that in this case, where we can write the following formula. I have written here this particular formula, which goes like this. Out of 4 bits, 2 bits are error prone. So this can be chosen in 4C2 ways, multiplied by the probability square. That means the probability that the success probability that has been squared, and the failure probability, which is 1 minus 0.1. It is getting the power of that is taken to be 4 minus 2, which is also 2 in fact. And see the similarity between the two answers. The way I dealt with the situation directly, I got the answer as 0.0486. Here in this situation also, we have got the probability as 0.0486. Now, what do we find out over here? In this case, you see that in this particular formula, we do not know what is the name of this formula, but we have known that in this formula, two important things have been taken into consideration. One is the number of times we are repeating the experiment and the probability of success. And for this, we have to know what do we mean by success in our case. Now, the same problem with the help of the following formula can be dealt very easily, and we don't have to write all this, we don't have to tabulate all these possible outcomes and sample spaces and events. We are relieved that we have ultimately got something, some sort of a thing is happening over here, some sort of distribution is this, which is actually following certain rule by which we can easily calculate the probability. That is happening over here. So now I'm defining some, now I'm observing certain things. What are these certain things? In this entire scenario, I have noted down a few important points. The first important point is that the number of times the thing was repeated, these trials, they are actually got a special name. It is called Bernoulli trials, by the name of the mathematician who is called Bernoulli. Also, we have observed that Just a minute. We have observed that the trials, they are independent of one another. I have already told you that. So I have highlighted this point that in these Bernoulli trials, all these Bernoulli trials are independent of one another. And in each trial, we are getting two different outcomes, two different types of outcomes. Either these outcomes are error prone or they are error free. So we can call one such outcome as a failure and another outcome as success. But we are interested in this case, we are interested in error bits. So we named the error bits as success. But in general, there are two types of outcomes. One is success and another is failure. So we have noted down this particular point. And another interesting point is that each time the experimented was repeated, the success, each time the experiment was repeated, the success has got the same probability. The probability of success is not changing. So probability each time you are receiving the bits, the probability of getting error bits is small p, which is 0.1. So the probability of success here, it remains constant. Now I am defining something which is written below. The random variable capital X that equals the number of trials that result in a success is a binomial random variable with parameters p lying between 0 and 1, because p is a probability, and n 1, 2, etc. The number of times you are repeating the experiment. The probability of mass function of such a random variable capital X is given by the following formula. Here fx is denoting the probability, and the formula goes like this. It is ncx p to the power x 1 minus p whole thing to the power n minus x, where the possible values of x are 0, 1 to up to n. It means either we have got in this number of experiments, we have got no success at all, which is represented by 0, one success, which is represented by 1, or all the successes which is represented by n. And why these terms small p and n? N is the number of trials and small p is the probability of success. Why are they called parameters? Because if the values of these parameters are not known, if the values of these parameters are not known, you cannot calculate this probability. In place of 1 minus p, one can put q also, because p plus q equal to 1. But we will not say that q is a parameter, because q can be calculated from p. That's why I have not written q over here. I have written 1 minus p. So binomial distribution has only got two parameters. One parameter is small n and another parameter is called small p. Parameter is such kind of thing by which we can identify the distribution. So if you give me a physical situation and you want me to calculate the probability, then as there are various such situations, various such different situations, they follow various such different probability distributions. So we have to know all the existing probability distributions. How do you know that a particular physical situation is following that probability distribution? Is by the fact that if you can identify the parameters, then for parameters which define a particular distribution, and if your physical situation has all the parameter values, then we will try to correlate the physical situation with the probability distribution of which the parameters are. Okay. Mean of the binomial distribution is is defined by the formula small n into p. Mean of the binomial variable. You already know that mean, by mean we actually mean here the expectation of the random variable. So if you consider the binomial variable capital X to be the random variable, its mean can be defined, is given by the formula n into p. So if you know the mean of the, if you know that the small n is there, if the value of small n is there and the value of small p is there, the mean of the binomial distribution, binomial variable will be np. So in our above case, since n is equal to 4 and p equals to 0.1, so in that case, your mean will be 0.4. So this is the formula, and variance of the binomial variable is defined by the formula np into 1 minus p. So sometimes we call it as npq. So you have to remember this formula. I shall not waste time by showing how these formulas are calculated, because since we'll be sitting for online examination where deduction of formula will not be asked. But this was a very famous and very, I mean, the examiners were kind of attracted towards this particular problem. They often said this as in the question, that how this particular formulae are calculated. So if you get to see the derivation of this formula somewhere in the book, you can study, but if you can't remember, then there will be no problem, because right now the situation is we are going to sit for online examination, and this type of descriptive questions will not be set, but you have to remember the formula. Okay, I am going to show you a very small board work over here at this stage. Say, for example, why am I saying that the formula is so important? I'm going to talk about that. Suppose I am asking you to survey a physical system. Okay, and after surveying the physical system, you have come to me and you have declared that the physical situation you dealt with, the variable present over there is the binomial variable. So the distribution is a binomial distribution. This is your declaration. Okay. Now, I don't believe you, because I know that you are not actually honest person. You can manipulate the data. So I am just trying to verify your claim. So what can I do at least is that I can ask you about the mean of that binomial variable and the variance of that binomial variable. Now, suppose you are telling that variance of the binomial variable is 4 and mean of the binomial variable is 3. Suppose your declaration is that you have calculated this thing. Then what can I check? I will immediately check that we know if your declaration is correct. So mean of the binomial variable is given by the formula NP, which is 3. And variance of the binomial variable is given by the formula NPQ, which is 4. But if I divide NPQ by NP, then what do I get? We get 4 by 3. That means the probability Q, which is the probability of failure, according to our notation, this is coming out as 4 by 3. But be it probability of failure or probability of success, doesn't matter. This probability is coming out to be greater than 1. And immediately I can understand my conclusion will be you are lying. You have not your claim is wrong. Rather, I must say that your claim is wrong, or you have manipulated the data. Or you may not have received the actual data. Okay, so in this manner, I can verify the situation, your claim. So this information about the mean and variance of the random variable is very important. So I'm stopping the share and I'm going back to the previous slide which I was sharing. Okay. Now, another question which I have discussed over here is the question goes like this. A multiple choice examination has 3 possible answers for each of 5 questions. What is the probability that a student will get 4 or more correct answers just by guessing? The current scenario in which I can study the same thing with you also. So suppose this is the situation. The multiple choice examination has 3 possible answers for each of 5 questions. What is the probability that a student will get 4 or more correct answers just by guessing? When I give you this particular problem or any type of this problem, and you already know that you have already come to know that there exists a physical situation, a system which follows binomial distribution with such and such parameter, and you do not know any other distribution. So what will you do? After getting this particular problem, you will say that, okay, let us check whether it is a binomial distribution problem or not. How will you check it? Okay, the process is, since the multiple choice question has 3 possible answers for each 5 questions, now you know that every student has to answer 5 questions. Means if you say that answering question is the experiment, he is repeating the experiment 5 times. So therefore here I have written the student's attempt is the experiment here, and I have written n equals to 5. So I have highlighted these things over here. And also I am writing that since they guess, but now students can guess the answer, or now in your case it is not happening. You don't guess the answer. Either you know the answer or you just do something else, which I don't want to say in this particular platform because the video will be uploaded in the YouTube. So anyways, so since the students are guessing the answers, all the 3 answers are equally probable for him if he guesses it. And therefore, he will think, since he is guessing, it's a very important fact. I'm taking some time to explain the situation to you. Probabilities are not calculated. We allocate the values, we allocate the probabilities. When you are guessing the answer, think about yourself. When you are guessing the answer, on the back of your mind, and nobody knows that, and you also know that, don't know that, on the back of your mind, you are thinking that I suppose all the answers are equally probable. And since there are 3 answers, I will allocate 1/3 probability to each of them so that the total probability is 1. So here he is actually saying his guessing is actually unbiased. So equally probable. So he is allocating the probabilities to each of the correct answers to be 1/3. And answering by guessing is the success here. So he is saying that the probability of success in this case is 1/3. Now, if X represents the number of correct outcomes, after guessing, he can get a wrong answer or he can get a correct answer. Now, if I'm interested about, again, you look at the question, we are interested about what is the chance that a student will get 4 or more correct answers. Okay, so I have to define the random variable, and you know random variable gives you the count. So here the count will be the number of correct outcomes he is getting by guessing. So since n equal to 5 and p equal to 1/3, these parameters are known. So we can try to apply binomial probability law here in this particular case. It doesn't mean that this particular problem cannot satisfy any other existing probability distributions. It may satisfy. You can do the same problem in various ways, but at least we are relieved that it can be dealt with a binomial probability law. We have all the facts, all the tools, so we can just apply the formula. Probability of x equal to x, small x, capital X is the mother variable that gives you the count of number of correct answers. And small x gives you how many correct answers. So he gets exactly small x right answers by the binomial probability law is given by the formula ncx, that means 5cx, p to the power x, that is 1/3 to the power x, 1 minus p to the power n minus x, that is 1 minus 1/3 to the power 5 minus x. So x equal to 0, 1, 2, dot, 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 up to 5. I have applied the binomial probability law here. And we are interested in the fact that the student will get 4 or more correct answers. 4 or more in this particular case, that either he gets 4 correct answers or 5 correct answers, because not more than that, because number of questions present in the question paper is only 5. Okay. This problem will not be applicable to you guys. Okay. The way you actually give exam, it's not like that. You are sitting in an offline situation, then I can apply the scenario to you. So probability of x greater than or equal to 4 is equal to probability of x equal to 4 plus probability of x equal to 5. And for each case, I can put 4 and 5 in this particular probability law. And that gives me the probability that he will get 4 or more right answers, which is 0.045267. In this way, by applying the binomial probability law, we can get the solution. Okay. Now, another alternative approach we can apply to calculate the same problem, a different approach. What is the different approach? You see, the number of experiment in the above example is n equal to 5, you know already. And the probability of success p equal to 1/3, as that has already been explained. So you know the mean of the binomial variable, if you treat it as a binomial variable, is given to be n into p, which is 1.667. That can be greater than 1 because np is the mean, it is not probability. Now we know that probability of getting more or 4 or more right answers is given by this. We can apply a different formula over here. So I'm giving you the formula in blue color. This is a new formula which is in front of you, where I'm writing probability of x equal to small x, which is defined as e to the power minus np to the power x by x factorial. A different formula I have presented in front of you. Here, the only difference is that in the binomial probability law, x were starting from 0 and it went up to small n. Here, x can take any value starting from 0 and it goes up to infinity. After getting this formula, when I am putting the same values, the same set of values over here, and we are calculating, then probability of x greater than or equal to 4 comes out as 0.081. Now, what was my earlier probability, which is 0.04, and what is my this probability is 0.081. Now, this probability law is not wrong, and that probability law is wonderful law. This can be very well derived for the same situation. By applying two probability laws, we are actually getting two different answers. Isn't it? Very strange scenario. Now, what to believe? should I apply this binomial probability law? And if I get this answer, is it correct? Or if I apply this probability law to this particular problem, and this probability law, I'm saying you, just take my words, it is also very well defined, whether this probability is correct. When I write 0.045, that means out of 1,000, 45 times it is happening, he gets 4 or more answers correct. And when I'm writing 0.081, it means out of 1,000, 81 times it is happening that he is getting 4 or more answers correct. So why is the above answer not matching with the answer obtained by using binomial probability law? The question which is coming to your mind. Okay, so this is you who is always there to confuse me also. Conditions under which the binomial probability law tend to follow Poisson law. So the probability which I have applied over here, probability of x equal to small x, and the formula, this is not a binomial distribution formula. Its probability is called the Poisson formula, Poisson. And this formula is defined in the following manner. I will define it. Below you can find the actual definition of the Poisson law. Now, binomial probability law and the Poisson probability law has an interconnection between them. In binomial probability law, n denote the number of experiments and p denote the probability of success. Now, if n is very large, which we denote by n tending towards infinity, and p is very small, which we which we are denoting by p tending towards 0. If this situation arises over here, the binomial probability tends to follow Poisson probability law. And here the product n into p is a very significant term. Okay, so if I define the product of the number of experiment and the probability of success by lambda, then if we have a random variable capital X whose probability mass function is given as follows, that it is defined as e to the power minus lambda lambda to the power x by x factorial, where x takes any value starting from 0 up to ... infinity, then such a random variable with this kind of probability function is called Poisson variable with parameter lambda. And since the possible values of x are discrete, are infinite, but they are countable, so these variables are discrete and the random variable is also discrete. A Poisson variable, Poisson distribution is another kind of discrete probability distribution. Time is almost over. In the next session, I'm going to explain about Poisson law in more details. I'm stopping here right now.